Let's get started. So we're trying to finish more selection that we started last time. We're going to look at error decomposition, which we looked at qualitatively last time. We'll look at a little more quantitatively today. And if we have time, we'll try to start with the theories, which is something that you really need to get from. Okay. So you're still working on your homework. I need to discuss a little bit. So we are running behind. So we missed the class. We're running a little bit behind. I need a catch-up lecture or two. So we have a couple of options. We can either schedule an extra class, or next week we can make it a couple of marathon sessions, which give us 45 minutes extra each time. That would put us on schedule. Thoughts? Preferences?
2 hours of class.
2 hours of class is too much. I should say I would put it in 2 breaks as opposed to 1. So show of hands, how many people would go for the 2-hour class? 2 hours. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, how many people would want a separate class? Okay.
Well, I have a class immediately after this too, like.
Oh, I see. You have a class immediately after?
Yeah.
Okay. Okay, I'll set up a poll. We'll have to find an intersection. That's what I did not want to do. I did not want to set up a poll, because there will not be an intersection. But okay, let's work at that. I'll ask that the intersection. But you should expect that somewhere in the next week we'll put in an extra class. Okay. On that note, so the week after spring break, your midterm will be held March 18th. It's in class. It'll be a pen and paper test. It's open book, open notes, closed internet. So you can bring in whatever you like. You can bring in anything downloaded, any of my notes, any of your notes, any book, anything. The test will be a mix of something like multiple choice questions, true, false, prove something, and what would happen for this data set. Like things, I'm not going to ask you to. There are obviously no implementations. It's just pen and paper, and I can't ask too many of proving type things, because then you'll be just stuck there. But there'll be sort of mostly intuitive type things, that if you understand what the problem is asking you, or what the optimization thing was asking you to do, then the answer would be clear for us and things. Okay. How many people have taken an open book test before? Anywhere? Okay. So most people have. If you have not taken an open book test before, if in an open book test you need to open the book, you're not doing too well. So it's not going to be things that, in case you haven't figured that out, we're not following any book anyway. I'm sort of cutting and weaving across a bunch of topics from a bunch of different sources. You're not going to find the things I'm asking directly mentioned or directly mentioned in there. So this actually makes your job harder, because it actually means you need to understand, not memorize. But I would still suggest come in prepared with notes and cheat sheets, even though you don't have any restrictions on them. You can bring as many as you like, but it'll still help you. Don't come with the entire Kevin Murphy's book and then start searching every time you see a question. It's not going to be a useful exercise. It's going to be an exercise, not a useful one. Any questions about that? Questions about the midterm?
No pseudocode?
I'm sorry?
No pseudocode?
Yeah, sure, pseudocode. I mean, questions of that type. Yeah.
So duration?
In class, so class times. So, whatever, 1 hour, 50 minutes. There's no break in between. You can step out. Alright, so let's look at where we were last time. So we had finished regression in the sense that we were looking at polynomial regression. This is polynomial regression one-dimensional, so there's a single feature x that's raised to some power, and we said that that's all fine. It may be polynomial in x, but it's actually linear in w. So if you just do a little slight trick. You define a feature map phi of x, which actually takes this x and just sort of outputs the the x raised to various powers. Since my function is linear and that, I can just pretend that's the features that you actually collected, right? So you can still construct a design matrix and everything goes through. We also looked at doing the same thing in multiple dimensions. So now x is no longer a scalar, it's a vector. It doesn't really matter. Phi can look at arbitrary entries in x and contain arbitrary combinations, and you can still sort of write them out on a matrix, and everything works out. We had ended regression at this point. I want to emphasize that we want you to understand a few different things about linear regression and about regression in general, which is all the connections that we told you between maximum likelihood and Gaussian distributions, least squares and Gaussian distributions, ridge regression, combining various priors, and what all of that means. We were using polynomial regression to look at the topic of model selection and understand the idea of overfitting and underfitting. Right? The reason why we were looking at that is the idea of multiple So we looked at this idea of polynomial regression in one dimension as an example for the task of model selection. And we somehow argued that this is a one-dimensional model class, this is a four-dimensional model class. If you keep looking at just the training errors, so just the fit on the training data, a larger model class, in this case a 12th order polynomial which contains 13 parameters as opposed to a first order class which contains only one parameter. So more parameter, larger model class will always do better. Notice that I can say always do better because there's a nested structure. But even if there was no nested structure, even if the larger model class did not subsume in it the smaller model class, I can say usually it will do better based on what kind of problems you tackle. Okay, and so the question is how do you then decide which model you're going to go with? Okay, and that's essentially the same question as picking hyperparameters or doing feature selection. And we had said the way you answer this question is not on training data because you have already used training data to estimate the parameters inside the model class. So now it is no longer a good metric for how well you're doing. So you have to go to another set, and you have to validation set, and that's when you have to. So you start off with multiple types of models, first order polynomial, second order polynomial. If you're doing classification, logistic regression, naive Bayes neural networks, whatever, you will tweak the parameters. You will fit the parameters of each one on training data. So now you have multiple parameters coming from different model classes. And you will evaluate those parameters on validation to know which model is doing better. Does that make sense? And ultimately, whichever model wins out, you have to use the parameter for that model trained on training and evaluate it on test to have an estimate for how well this model class with this parameter is going to do when you ship it out. And that's why, so there's a minimization done here over parameters, minimization done here over model classes, no minimization done here. And that's sort of crucial. Otherwise, you can't trust that one. Okay, if you don't have enough data, then we discuss the trick of cross-validation. So you divide your data set into folds, or a single fold, a fold of size 1, and then you iterate over the folds. Okay, So we talked about the idea of overfitting versus underfitting, and that's where we're starting off today. Let me talk about error decomposition first. So we talked about how. So in general, the behavior that you're going to observe is in polynomial regression. I can plot D here, but in general, this can be a measure of complexity of your model class, right? I have not told you how do we measure complexity for arbitrary model classes. We know for polynomial regression, D, that number is a good measure, right? In general, you will observe trends like these, where the training error will go down as you have a higher, more complex model class. Okay? This is E-train. Validation errors that held off will, in general, show some sort of a trend like this. And there will be two regimes. This would be the underfitting regime, and this would be the overfitting regime. The underfitting regime is when you're doing poorly in terms of the training error and in terms of validation error. That's when you're using too simple a model. You need to sort of expand your model class, add more features, go to nonlinear feature maps or something. If you're in the overfitting regime, that's when you're doing really well on your training data, so your model is explaining or working really well on your training data, but really poorly on some held out validations. Right? That's when you know the complexity of your model class is too large. It means that now you need to do things like feature selection, dimensionality reduction to reduce the model complexity, and there's a sweet spot somewhere. Okay? The thing to notice is that the validation error or the error on held out data is high in both cases. Right? You created whatever you did, you shipped it out, and the number you got back was large. And in both these cases, it's large, but it's important to distinguish those two cases because the response that you need to take as an algorithm designer is completely different in the two. Right? In fact, what we'll try to do today is try to tease out this validation error, like high validation error, into two different sources. Right? One source will be called the bias of your model, and one source will be called the variance. And roughly they will correspond to the ideas of modeling error or estimation error. It's a coarse correspondence. So you can be performing poorly because your model is. So notice that when D is just 1, there are two parameters that you have to learn in terms of polynomial regression, W0, W1. When D is something like 100, there's a 101 dimensional vector that you have to learn for polynomial regression. Fewer parameters here, so you will need less data to estimate these parameters. So your estimation error or your variance in your model will be low, right, for this sort of a case. But your bias or your modeling error will be high. And it will be the exact opposite in the overfitting case, because when you're overfitting, you will actually, your model class is really large, you will actually have a really low bias, and I'll explain formally what a bias is, but you will have really high estimation error, which means if I give you one data set and another data set, your results will be really different between the two. Because you have to fit a lot of parameters, and the amount of samples that you're seeing are too small compared to the number of parameters that you have to fit. And the results that you will see will be extremely different based on what data set you saw. Does that make sense? Mm-hmm. So this large number will be teased apart into two different numbers, and only one of them will be large, the other one will be small. And somewhere, this is a trade-off, and if you want to minimize the sum of two terms, somewhere in here will be something that has small modeling error, small estimation error. Right? Does that make sense, roughly? So we were talking about error decomposition last time, and last time we were looking at it really qualitatively, that there's some model class, reality usually does not lie in your model class. Model class has various models in it because each one corresponds to a different parameter setting. Your goal is to find the best one in your model class that minimizes, that's the modeling error, right? That you have to pay that. But then you're also paying the estimation error. And the reason why it's estimation error is if I give you one data set, this is what you will find. If I give you another data set, maybe you'll find something else. If I give you another data set, maybe you'll find something else. If I give you infinite data, you will actually find that. But each one of these samples, these data sets, is some finite size data set. Right? So you're actually getting multiple estimations based on which data set you saw. Right? So in fact, if you take your data set and you split it up into multiple folds or multiple, so if you permute your data and split it into train and val, if you do multiple permutations and just train on train, you will actually land at different places based on that split. Right? And when you, so that will be the idea of variance. And we talked about optimization error that we're ignoring for now. That this could be an NPR optimization problem. When you shrink the size of your model class, so this was a 14th order polynomial, this becomes a 10th order polynomial or a second order polynomial, there are only two parameters, let's say you have to estimate. When you see different data sets, you don't have a lot of estimation error because the answers that you get are tightly clustered together. Does that make sense? But they may be tightly clustered together, but really far away from reality. Make sense? Okay, and the opposite scenario will happen when you enlarge a model class. All right, so let's do this a little more formally. So we'll define two terms. One will be this idea of bias, one will be variance. Bias will loosely correspond to modeling error, and variance will loosely correspond to estimation error. Bias formally will be the difference between what you expect to learn and the truth. And I'll write that formally in a second. And it measures how well you're doing with respect to to represent the true solution, and it decreases with complex models. And so as the model class increases, bias goes down. Variance is the difference between what you expect to learn and what you learned from a particular data set. So across data sets, what are the changes happening between what you're estimating? Does that make sense? And it will increase with more complex models. If your model is really simple, then there's not much variance in what you will estimate. All right, so let me do this with a particular example. Let's go back to the simplest case of a back to the simplest case of a coin toss, and I'll write down what a bias and variance is in terms of a coin toss, right? So if you recall, there was a single random variable. It took two states. It says 0 and 1, and we said y was distributed Bernoulli, let's say with some unknown parameter theta star, right? We don't know what this coin is. It has some parameter theta star, and what that really just means is that the probability of observing heads is theta star. Right? We don't know what this is, but that's the coin given to us. And probability of observing tails is just 1 minus theta star. Right? We don't know what these numbers are, but that's the coin that was handed to us. And what do? Well, you ask for a data set, and you wrote down an estimator, right? You had theta hat MLE, which we derived as 1 over n summation of yi. Right? Give me a data set, I'll count the number of heads or ones, and that'll be my estimate of this number. So let's say this is one data set. Heads, tails. It's a data set of size 3. I'm only going to write down a couple of data sets of size 3, but you can imagine this is for larger size data sets as well. Right? Given this data set, what would you estimate here? You'd say, okay, 2 by 3. Right? You count 2 heads or 2 ones if you'd like me to write that down clearly. And this is also 1, 1, 0. Right? Here's another data set. Let's say tails, heads. Right? It's a coin, it's possible. You don't know what theta star is. It's definitely possible that this is data set 1, this is data set 2. Here, what you would estimate is 1 over 3. And I give you a third data set, which in this case was heads, tails, heads. And you again estimate 2 over 3. Okay? notice that your estimate is changing as a function of the data set. The data set is random, therefore your estimate is also a random quantity. Right? So if I think about the number line between 0 and 1, theta star is some quantity. We don't know what theta star is, but based on the data set you get, you make one guess, right? In one case, you guessed 2 over 3, in one case you guessed 1 over 3, and in another case you also guessed 2 over 3. Right? So you make multiple guesses based on the data set. This was your MLE estimator. How about I come up with a theta hat, I'll call it theta hat lazy. This is a lazy estimator. What it does is, I'll just take whatever the first value is. If it's 1, I'm going to predict the coin has probability 1. If it's 0, the coin has probability 0. Right? So this is a theta hat which is just y1. Just look at the first coin toss. In this case, it's heads. So alright, I'm going to guess this coin always gives out heads. If it's tails, I'm going to guess this coin always gives tails. If it's heads, always this. Okay? So this is a perfectly valid estimator, right? It's not you'll see it's not a good estimator, but it's a perfectly valid estimator. Here's another perfectly valid estimator, which is just downright silly. Always says 1. The coin is just always has probability 1. I don't really care about your data set, you and your data sets. I always answer 1. Okay? And you can ask the question, I was talking about the fact that this number varies as the data set varies. So you can ask the question, well, what is the expected value of any of these estimators? Expectation under what? Expectation under the probability of the data set, right? So I give you a data set, you come up with a different number, what is the expected value? Which means if you just average, each of these data sets have some probability. If you multiply those numbers and you average this out, what is this expected value? It's actually really easy, it's not too difficult to compute this for each of those estimators. So this one, which is theta hat MLE, is actually the expected value 1 over n summation of yi. Right? Linearity of expectation, I can move expectation inside. And so that will give me 1 over n summation expected value of yi, where I goes from 1 to n. What is the expected value of observing, right? What is the expected value of a coin toss? Right? It's just 1 times probability of 1 plus 0 times probability of 0. We know probability of 1 is theta star, whatever the true answer is. Right? So this is just 1 over n summation of theta star. Right? So this answer is just theta star. Which is just saying, if I think of this as a histogram, every time you get a data set, I plot down a number, and so it becomes a histogram of your guesses. Your histogram is centered at the right place. Right? So the expected value of your estimator is actually reality. This is what we wanted to estimate. On average, your estimator will give me the right answer. This is the concept of unbiased. Right? Your estimator is not biased. The difference between what you expect to learn minus reality is 0. Does that make sense? Okay, so there's no bias in this model. How about this one? So expected value of theta hat lazy. Maybe do you want to tell me? It's also unbiased. Why? Because this is just expected value of y1, right? It doesn't really matter what the rest of the data set does. It's just expected value of the first one, which is also theta star. So it turns out this estimator is really nice. If you had infinite data sets and if you just average across those, this would work fine. On each data set, it's completely wrong, unless your coin is completely biased. Right? But across infinitely many data sets, it's perfectly fine. So this is unbiased as well. What it's going to have is high variance. Because if you think about the histogram that you will draw for this type of an estimator, it can only have bins here and here, right? It can only predict 0 or 1. Yes, it does center at the right place, but it has extremely high variance. Right? So between one data set and another, you will end up predicting extremely different quantities. Right? Does that make sense? Is this one biased? As long as theta star is not 1. A broken clock is correct twice a day. So theta hat silly is expected value of 1, which is not equal to theta star if theta star is not 1. Right? So you have some bias, 1 minus theta star, whatever that is. I mean, this is what the histogram of this one looks like. The histogram of the third one is just a single peak at 1. That's all it can predict. Turns out it is also extremely low variance estimator. There is no, doesn't really depend on your data set. It's extremely low variance, always gives you the same answer, just that answer could be arbitrarily wrong. Not arbitrarily, or at max, the answer is going to be wrong by 1. Okay? So the reason why we looked at these three is that this one has low bias but high variance. Right? It is actually unbiased. It's about as low bias as you can get. But it has extremely high variance because if you looked at how it's changing across the data set, that's extremely high. This one has low variance but high bias, potentially high bias. And turns out that this one has low bias and doesn't have too large a variance either. We're not looking at that issue today. That makes sense? So we've teased apart these two issues. This was all for the case of just probability of y. You can also look at this for the case of probability of y given x, which is regression or classification techniques. That makes sense? Any questions? Actually, before I forget. So if you
quantify the bias or unbiased by this formula, and how do you calculate the variance, the specific?
Sure. So the bias is expected value of theta hat minus theta star. So the difference between what you expect to learn minus reality and variance is just expected value of theta hat minus expected value of theta hat squared. Right? It's just, this is just variance of a random variable, and that random variable just happens to be your estimate. Right? These are a bunch of random variables, y1 through yn, those are random variables. This is a function of the random variable, therefore also a random variable. And this is just the definition of the variance of a random variable. That makes sense? Okay.
Can you say again why the expected value of the lazy model is still the same as the expected value for MRE?
So it's right here, right? There's nothing much to it. What it does is just copies y1, right? It just looks at the first value. So we're just talking about the expected value of the first coin toss. And what is the expected value of the first coin toss? It's probability of 1 times 1 plus 0 times probability of 0, and the probability of 1 is theta. So on average, across the data sets, across different data sets, the first coin toss will be heads just about as many times as that coin can lead to heads on average. Does that make sense? Because the first one isn't special.
So is it possible that the bias or the variance is a function of the truth, the theta star?
So bias is a function of the truth, right? It has the truth in here.
So in this case, how to evaluate,
Right, so how do you know which one is better? You have to talk about the worst possible case. So you have to assume, so one of the things that people do is, what could the bias be? How large could the bias be? Right? So if you think about this one, this has 0 variance. It could have 0 bias, but you have to talk about how large could that bias be. Right? If you think about any of these guys, no matter what theta star is, their bias is always 0. So you're going to talk about the maximum possible bias against all possible realities. That makes sense? Okay. So like I said, this was all in the context of coin toss, but you can have these same arguments in terms of regression. And I can show you a demo. For a MATLAB demo. Why do I have to do it again? Okay. So I'm interested in running, long distance running, like half marathons, that kind of stuff. And if you actually read about half marathon running, turns out that if you plot people's max running speeds over age, it's one of those sports where you can be competitive. Like people peak not in their 18s as opposed to other sports, but apparently the fastest half marathon times are around 29 or 30. But it's actually true. I'm not making this up because I'm old. This is it's actually true. The trends are true. The actual numbers, whether or not it's 10 miles per hour or 12 miles per hour, like that's it's actually slightly faster. People like the half marathon times are somewhere upwards of 13 miles per hour, right? But there's also a long tail. People don't lose their abilities in long distance running for a long time. And if you've ever been out on a trail, when you see a 60-year-old pass you, and you're huffing and puffing, it's really disappointing. But this is roughly, we don't get to change the reality, right? This is reality. Okay? You don't know what this reality is. You're trying to estimate this reality. Okay? So what do you do as an experiment designer if you're trying to estimate this reality? You ask people to come in for a study, put them up on a treadmill, and measure their times. Okay? So this is what that looks like. So you conducted 2 studies on 2 different occasions, right? Because funding came in for one and then it stopped, and then funding came in for another and then that stopped. But you did 2 different studies. Here's, each X is a participant. You had 20 participants who came in. Maybe on one of the studies, a whole bunch of geriatrics came in. They were just off that day, so you sampled a lot of data here. And notice that the blue is still truth. You don't know what that truth is. You just know what the samples tell you. And another day, bunch of younger people came in, and that's what it is. So you have 2 data sets. This is D1, this is D2. And your task is to find out what this reality is. What is the real curve? So here's something that you can do. You say, okay, I've learned polynomial regression, or linear regression first. So I learned linear regression, and here is my fit to this data set, here is my fit to this data set. This is an extremely simple model class. Linear regression, 2 parameters, you're going to have low variance. So the 2 estimators of W1 and W2 on 2 different data sets are not going to be that different. There's low variance in that estimator, but there's high bias in the sense that the distance of reality from your model class is large as measured by the losses that you're making. You're not explaining this data very well. Right? You could not explain the fact that people actually get faster till they're 30. You're just saying the fastest person is a 10-year-old, and then it's just all downhill from there. Okay? This is what you come up with. It's not a good model for reality. And then you realize, oh, I will start polynomial regression. How about... not that. Oh man. Give me a second. Demo failure. Okay. So that was linear regression. Here's polynomial regression. Right? You go ahead and you fit a 15th order or whatever, 20th order polynomial, perfectly explains every single data point. If you compare the 2 polynomials that you have learned between the 2 data sets, they are extremely different. One of them one of them has a dip here, one of them just goes down really low to like a 4 miles per hour here, goes really high up there, somewhere in between age 10 and 11. This one does exactly the opposite. Right? So if you pick a point here, age 11 or 12, the prediction made from this model and that model are completely in disagreement. Right? That even though the curve of these lines is different, the straight fits are different, their actually predictions are not that different. So if you actually pick 20, the numbers that they're predicting are quite similar. So a smaller model class has lower variance, a higher model class has higher variance, but it actually has less bias. Right? It's actually explaining, if you had infinite amounts of data sets and you were able to average these blue curves across all of them, you would actually have a very good estimate of reality. But you don't have infinite data sets, you just have 2. Right? And that's why that's a bad fit. Here is, for example, a 4th order polynomial, which between 2 different data sets doesn't change much, so it has low variance, and it has low bias as well because it actually does a decent job of fitting these points. Does that make sense? So if you think about that underfitting, overfitting curve, on the left we have high bias, on the right we have high variance. Somewhere in between you have a model like that which has both low bias and low variance. Does that make sense? Here are those 2 predictors which you learned to do of the 1st order. Here are those 2 predictors, the 15th order predictors. You can see that the difference between the 2 first order or first order polynomial predictors is large, the variance between the 15th order is large. And here are the 2 4th order predictors, right, on 2 different data sets. So the variance is small in the 4th order case. That makes sense? Okay. Okay, and so this is going to, in general, these are some of the debugging tools that you can use to study which scenario you're in. Because often the most common scenario is you try something, it doesn't work. But that's not, like, you have to, what you can try to debug with it is, if you resample your data set, if you try on a different form of the data, are you getting significantly different predictions? If you are, then you're probably working with something that has high variance. And that's the overfitting case, you probably want to scale your model class down. If you're in this case where different samplings of the data set are not giving you 2 different predictions, then you're in the high bias case, low variance case. Right? Does that make sense? Okay. Here's something else that we can look at, which is a common debugging tool as well. These are known as learning curves. So this is another quite useful debugging tool that you can use. These are called learning curves. What you do is on the x-axis you plot n, or the number of samples, or the amount of training data you're using. So maybe you have a large data set, but what you go ahead and do is you subsample that. So you take a 10th of that or a 20th of that, and this is what you're doing in your homework as well. And so you start with training on a small amount of data, let's say as little as 1 sample or 2 samples. Right? And think about it this way. What's going to happen? You have 2 possible cases. Sorry, this is another curve. I'll explain. So this is x, this is y. Let's say this is reality that you're trying to fit with regression. Right? There's a 1-dimensional x, 1-dimensional y. It is clear that this is not it doesn't look like this is a linear problem, right? But you still go ahead and fit this with a linear model. You're going to get some sort of a fit, and you're going to make some sort of errors. Right? your learning curve is what does your training error look like and validation error look like as your number of data increases. And these curves generally look like this. So if, let me actually finish this point and then stop. So if you have a simple model class, you will often find that both your training error is high and your validation error is high. This is all error. If you have a simple model class, you will find that both your training error is high and validation error is high, and they stay high even with large amounts of data. Why is this the curve? Because when you have small amounts of data, when you have a single sample, you'll do really well on your training data. If you remember k nearest neighbor, if you said k equals 1, you were getting 0 error on training, but you'll do really poorly on validation. Right? As you see more and more data, the difference between val error and train error will nearly go to 0. There will be no signs of overfitting. There's no difference between the two, but your train error will be high. Right? Just this absolute value will be high. On the other hand, if you actually go ahead and fit this with an extremely powerful model, where you're overfitting, you will observe trends like this. You'll observe a trend that roughly looks like this, where this is n for number of samples. You'll again notice that initially you have small training error. This is val. You'll again notice that initially you have small training error and it does increase. It goes beyond 0, for example, but your training error will continue to stay low and there will be a large gap between your training and validation error. And it'll be the same trends. These trends are pretty similar. The only difference is that the training error is small and the gap is large. And there, the actual training error is also higher and the gap is small. Does that make sense? You can often look at these curves and try to diagnose, are you in the overfitting case? This is the overfitting case, and this is the underfitting case. But if you're here, then you probably need, there's very little left. The fact that there's a gap here is because you're not learning from infinite data. If you had learned from infinite data, then there would be no gap between validation and training. Right? There's very little left, so more data will not help. Right? If you find yourself in the underfitting case, you should not feel the impulse to go out and collect more data sets. Right? It's not going to change your results. You'll find, whether you train a linear fit to a line with 10 points or 10,000 points, you won't get two different answers. Right? It is this sort of a case where you can expect improvements with more data, because these curves are actually going and getting closer together as you get more data. Does that make sense? And if they are not progressing fast enough, then you probably want to scale down the complexity of your model class. If these curves are not getting together close enough, then you have still far too many parameters based on how much training data you have. That makes sense? Okay, let's give it a couple of minutes here.
So in between, right? They will get closer and lower.
Yeah.
So what underfitting happens here? Similar figure, but higher.
So this is underfitting. Yeah.
So this is actually underfitting.
This is underfitting. Train error is high. Value error is high.
So what was the optimal case?
The optimal case would probably look like you have this is low and this is low, so that the gap between them is small and the absolute value is small. So this is small and the gap is small. So you're doing well on training and on.
So the way to prevent overfitting is that cut it off once the gap is small enough under a threshold.
Yeah, so this is what we were talking about. If on the x-axis you have the complexity, right? The complexity of the model class. Then you're going to see this is the training error, this is the validation error. So you'll stop you'll reduce your model class when the validation error starts rising.
Is there a way to move that point up?
is what
Yes, sir. Yes.
but this error.
Oh, excuse me, go down.
So at some point you're
Playing with your data and
at some point you're hitting up against something called Bayes error, right? You cannot move this down more than some number. That's the best you can do. Because even if you have infinite data, even if the model class is large enough, reality may be probabilistic. So there's so much you can
And
do.
so I'm trying to choose,
Thank you.
basically say, all right, I have two wells, I require regression tools, I have some data. So I'm going to click apply, overfitting
Some large model. It depends on one
I want
problem.
to prior.
And the other one is
If I see
something
these like
real.
variables,
Something
like
like
the expected value.
When you increase the order of polynomial, what do you actually increase?
what are you increasing?
Yeah.
You're increasing the weights, the length of the vectors. So polynomial of order 1 has only two weight numbers. It's still powerful. It's 0 to numbers you have to fit.
Is Bayesian?
I have another question. So this way to prevent overfitting is in terms of the complexity, like the order of this model. Do we need to consider how many examples, how many samples we're using here to prevent overfitting? I have 1,000, but I just use 500.
You can kind of looking at these points, right? Sorry, let me answer that once we get back. So yeah.
As the number of samples increases, is it always guaranteed that the training impacts
No, because at some point, as you don't asymptote to infinity, it has to asymptote to some value, and that value is the best you can do. Approximation.
no matter how much your number, as you increase number of samples, no matter how much you randomness.
And I'll do my graduate thesis class, I watch YouTube so much. It's so cool, some of the stuff you do.
Okay, so there were a couple of questions asked here. So there was one question about does this curve usually asymptote, or is it going to infinity? This curve has to asymptote at some point. It won't go to infinity because if you think about it, this is the size of your data set, right? If you have infinite data, then what you're recovering is the best possible model in your model class. Right? So at some point it has to converge to that if you have an unbiased estimator or if you're consistent estimator. There was another question that was asked. What were you saying? So about the validation versus training error plot. Was that your question? Am I
I'm
forgetting?
just wondering, so if you have the samples more than enough, how can you decide that how much we use will be enough?
So if you have a large data set, do we start using all of that
Yeah.
at once? Exactly. So that's where learning curves come in, right? What you want to do is you want to plot even if you have 1 million data points, what you want to do is you want to start small and keep training on larger and larger points and figure out what your training and validation curves look like. Because if you have already reached this best case scenario where you are happy with this validation, so this is eval, this is e-train. This is the best case scenario in which there is very little gap between validation error and train error, and they're both small. You're happy with this performance. At this point, adding more data is not going to help.
Perfect.
Does that make sense? Okay. Let's see. Okay. So all of these debugging tools are actually quite useful because when you start building your algorithms, you'll be faced with sort of this. This is a typical conundrum, right? You'll try something, it's not working, and you have a bunch of options that you can do. You can add more training data, use smaller set of features, larger set of features, lower the regularization, higher the regularization. Right? You can play with a bunch of axes, and some of them will just not make sense based on what you're facing. So should I get more training data? Well, that depends. Are you in the underfitting regime or the overfitting regime? If you're in the underfitting regime, there's no point getting more training data. Your model is simple. There's not anything else that you're going to extract from it. Should I use this? Should I do feature selection? Again, depends. Are you in the underfitting regime? There is no point doing feature selection, because if you're already underfitting, dropping features is not going to give you. You're shrinking the model class. You're not going to improve performance. You want to do feature selection when you're overfitting, and the opposite in the case of larger set of features. And it's something similar with regularization. If you remember, we talked about least squares as with a Gaussian prior. We talked about nested model classes. So there's a 15th order polynomial which contains in it a 14th order polynomial all the way down to this. And we talked about loss plus lambda times regularization, where regularization was just the norm of the weight vector, right? Norm squared. What is this doing? If you remember, the 0th order polynomial is just a zero norm vector, right? It just contains zeros everywhere. In terms of polynomial regression, a 15th order polynomial is a weight vector with 16 entries. It contains a W0 all the way till W15. If you set this last entry to 0, you're now in the 14th order polynomial. Not the 13th order polynomial. So the all 0 vector is the 0th order polynomial, or it's the special case, right? So by adding that regularizer with some strength, you're actually doing soft model selection, because you're searching in this, you may start with a large model class, something like a 15th order polynomial, and you may actually say, I actually put you there's a lambda times norm squared penalty. So as you go away and away from the 0, you pay a penalty for that, right? So the strength of lambda is actually how strongly you want to be close to the 0 vector, or a simple model. And so you want high strength, so you want to increase lambda if you have too simple a model. Sorry, the other way around. You want to increase lambda if you have overfitting happening. Right? If you have a weight vector and you're overfitting, increasing lambda will push you more towards the simpler model. So higher regularization is needed when you're overfitting. Lower regularization is needed when you're underfitting. So you want to search in a larger space without penalizing. Does that make sense? Okay. Okay, so at this point, we're done with this idea of model selection, and we're done with sort of this module, if you will, of error decomposition and cross-validation, right? We expect you to understand these ideas of approximation, estimation errors, and the difference between train test expected and cross-validation. There is going to be something in the notes about the bias-variance trade-off for squared losses, which I have to skip because I want to get to the naive base part, but it's a really simple derivation, and please look at my notes when you go back. Okay. All right, so let's move on. So now we're really getting into, we looked at your first regression model, linear regression, polynomial regression. Now we're moving to classification. So it's the mapping from X to Y, and we're going to do that with the simplest classifier of 9 things. It's going to be your first probabilistic classifier. Note you have met a classifier before, you can do classification with nearest neighbor. This is going to be the first probabilistic classifier. Okay. Actually, let me just do something easier. Okay, so here's the setting. Your features are going to be X in some d-dimensional space, and Y for us is now going to be some discrete number of classes, right? It's going to be 1 through k. This is not a continuous value now. This is k-way or multi-class classification. This would be binary classification, in some cases we write the isomorphic form with +1 -1, right? This is going to be binary classification, this will be multi-class classification. If you notice that one key object that kept coming up in a lot of these discussions was the posterior probability of y given x. In k nearest neighbors, for example, we told you that you could just count the number of, let's say it's y equals little y, right? You could count your neighbors and check which one of them had class y divided by k, right? In nearest neighbor, you could use the proportion of neighbors with that category divided by k as some sense of a confidence of how confident you are in this category. Does that make sense? In regression, you also dealt with this object, but we had, y given x equals little x was actually a Gaussian. W transpose x equals sigma squared. Right? If you remember, we said probability of x given y comes from some Gaussian with this mean invariance. So it's clear we're heavily interested in this sort of an object. If for the input x, I can form a distribution, in this case, length k vector, right? And there are some numbers here that sum to 1. If I can find the posterior distribution of what do I believe about various categories for this input, then I can just pick the one with the highest belief. Right? And so it comes down to this problem of finding this belief. In nearest neighbor, you were just looking at the neighborhood in some feature space and you're just counting. With naive Bayes and probabilistic classifiers, we're going to actually have a probabilistic model, and we're going to say, this comes from some model. Right? Nearest neighbor was a non-parametric classifier. Does that make sense? Once we have this, we're going to just use argmax of y. Right? This is going to be your prediction of that, if you will. Okay, so let's think about, so this is actually going to lead to a certain divide. And the divide is going to be between two kinds of classifiers. So this is x1, this is x2. This is the data set, let's say, you're dealing with. This is the data set you're dealing with. This is a supervised learning problem. You know what the labels are. This is all the data points. This is a two-dimensional feature space. You're measuring two quantities. This is all data from one class. This is from another class. We are interested in computing, probability of y equals little y given x equals little x for any point x, right? There are going to be two approaches to doing this. The generative approach and the discriminative approach. The generative approach is going to, and I'll tell you why it is a generative approach. The generative approach is going to say, well, I'm actually going to use Bayes' rule. So I know that this is equal to probability of x given y times probability of y divided by probability of x. Right? So I'm going to estimate from my data probability of x equals little x given y equals little y. And I'm going to estimate probability of y equals little y. I'm going to estimate these two terms, and then I can multiply them, compute the posterior, do the argmax, and that's how I'm going to make a prediction. Right? And the discriminative approach, this is going to feel a little unnatural, because it feels, why did we have to estimate these two quantities, why not this directly? And that's what a discriminative approach is going to do. It is going to directly estimate the quantity that you care about. It is going to directly estimate the posterior, or sometimes not even estimate the posterior, but directly estimate a mapping which is not going to have a probabilistic interpretation. So it's going to just directly estimate g of x to y. Right? There are going to be two distinctions there. In terms of that figure that I've drawn, what would a generative approach mean? It would mean that you estimate the mean of this class. Right? This is class 1, this is class 2. So you estimate the mean of this class, and maybe you estimate the covariance of this class. And then you fit a probabilistic model of what do the features look like for class 1, what do the features look like for class 2. The features x1 and x2 have means here, and they have this sort of a variance. So you try to explain your data for two different classes, and you measure the prior of those two classes. Does that make sense? And the discriminative approach directly goes for either a posterior or some sort of a function that separates one class from another. So it's a function, so g of x is positive. So this is the g of x equal to line, and it's the g of x will be positive here and negative here. It's just some function that separates one class from another. Does that make sense? The reason why this is called a generative approach is because you can sample, after you estimate these matrices or these quantities, you can create new data sets. Right? You can sample a y, given y you can sample an x. In this approach, you cannot explain your data. Because you do not model probability of x. Right? So all you can do is, if given an input, you can actually tell what the output should be, but you cannot sample new inputs. Right? So if you're not interested in creating new dataset tasks, if all you want is prediction, then this route is often suggested. That make sense? Okay. So what we're going to do today is start with this one. This is going to be, the example that we will see today is a naive Bayes classifier, which will be a generative classifier. And next time, we'll see an example of this one, which is a logistic regression classifier, and this will be an SVM. So this will be today, and maybe next time, and that's the next we're going to define an SVM. And along the way, we'll actually make connections. We'll talk about logistic regression being, it has certain specific connections to naive Bayes. That make sense? Okay, so let's try to think about this approach, and let's try to think how you would come up with these numbers. So this was the continuous feature case. It's too difficult. You have to assume Gaussians. Let's start really simple. Let's say that your features are actually binary. So you actually have x1 all the way to xd, and they're all between 0 and 1. This is just some binary thing you measure. Like, does a house have whatever? Right? It's just binary, and y is kb. So we have to estimate a prior probability of the classes and the probability of features given the classes. How many parameters do I need to estimate this? How many numbers do I need to estimate from data? It's a vector of length k, right? How many numbers do I need? Not a trick question. K minus 1, thank you. So this is the probability distribution. It's a vector of length k that sums to 1, k minus 1 parameters here. How about this one? The probability of x1 equals little x1 all the way till xd equals little xd, given y equals little y. How many? This is a table. This is a really massive, multi-dimensional array, right? It has d coordinates, and there's one of those tables for every category. How many numbers do I need to estimate here? Come on. It's a large table. How many entries does that table have? N. So n doesn't exist here. D is the number of features. So you have x1th dimension, you have x2th dimension, x3 dimension, and it's just, every dimension has just 2 cells, right? How many cells are there in this multi-dimensional matrix? 2 raised to d, thank you. 2 raised to d. There are 2 possible entries, d of these, 2 possible elements, d of these, 2 to the d. So how many free parameters? There's one you get to save. 2 to the d minus 1. because they must sum to 1. And you missed a k because you need to learn k of these 1 for every 1. Does that make sense? Think about if you had two features, x1 and x2, this would just be a matrix. x1, x2, it would have two values, 4 numbers, and you would need one such matrix for the class y equals positive, and you would need another such matrix, x1, x2, for the class y equals negative. 2 to the 2 minus 1, 2 to the 2 minus 1 times 2, which are the number of categories. Okay, so you need that many free parameters. 2 to the d is not happening. It's just, you don't have enough data. If you measure 100 things, that's more than what, the number of particles in the universe or whatever, I don't know, there's something like that. Right? You're not going to measure that much data, so you will never be able to fill these matrices up. Right? Because what is it asking? It's asking if I observed feature 1 to be plus, if I observed feature 2 to be minus, if I observed feature 3 to be plus, then go to that entry and then maybe increment a count if I'm keeping a count of how many times have I observed that. There's going to be a whole bunch of entries that will stay 0. You will just never observe those counts. Right? So this matrix will be largely 0. You just won't be able to estimate this matrix. That makes sense? So what can we do? How do we, what is the usual common trick for reducing the number of parameters in a probabilistic system? Assume independence, thank you. Assume independence. So here's the independence that we are going to assume, and this is going to be the independence that naive Bayes assumes. It's called naive, perhaps insultingly, but it actually performs quite well. Here's the independence that it assumes, that this joint distribution actually factorizes into probability of xi equals little xi times y equals 1. I going from 1 to 2. Does this make sense? That the features conditioned on the class are actually independent, and I can just multiply their probabilities. Right? Note that this does not mean that probability of x1 given little x1 times x2 equals little x2 is the product of. This does not mean this factorization happens. It does not mean that your features are independent. Right? This is not the assumption being made here. What is being made here is if I tell you what category I'm talking about, if I think of the two-dimensional case that I was drawing, it's +1 and -1, so we're back to the continuous case in terms of features. These are the two-dimensional things. What I'm assuming is that if I tell you that I'm talking about this category, knowing x1 does not tell me anything about x2. So the spread of this cannot be, it has to be axis aligned, basically. That's what you're assuming. But the spread of data for each class has to essentially be axis aligned. It can be axis aligned like this, or it can be axis aligned like this, but it can't be diagonal, for example. x1 cannot tell you anything about x2 if I tell you what category I'm talking about. Does that make sense? Yes?
So, I remember I read in the book that that they're independent, right? That means that
They're conditionally independent.
yeah. Okay. So that if you know the relationship between one, right, doesn't tell you additional information that you could tell from the other, right? So does that mean it could actually be aligned, but
So what is the question?
so you just said like it cannot be aligned, like
I said if you know the features are Gaussians, like if it is a spread, then they have to be axis aligned. They cannot be.
okay, yes.
Yeah, they have to be axis aligned. So if I'm plotting x1 here and x2 here, and you know, it cannot be this case because this case And this case means that this is the data set which is y equals +1. So clearly, if I tell you the value of x1, you know something about the value of x2. Right? It cannot be that case. So the naive Bayes assumes that your data set is not like this. Naive Bayes assumes that your data set is like this. So these are axis aligned. Notice that the spread or the scatter or the Gaussian covariance, whatever, it doesn't have to be circular. The variance doesn't have to be same in every dimension. You can have this sort of a variance. So x1 can be, have larger variance than x2. It's just that no matter what value of x1 is, it doesn't tell you about the value of x2. Right? They just cannot have a linear relationship or any sort of relation. Does that make sense? Okay. So a generative approach estimates these two quantities, probability of x given y and probability of y, and uses the Bayes rule to finally make a prediction. So what it does is it looks at the log probability of x given y plus log probability of y. These two multiplied together are proportional to the posterior. You look at the R max. A discriminative approach directly estimates V of them. The differences between the two are that generative feels indirect, but in the end you can generate a sample. And so anytime you're talking to people in biology or any of the natural sciences, they will often prefer that you use a generative approach so that you can, maybe you can create new data sets and you can look at the kind of samples that your model is generating to check whether it is physically or biologically plausible or not. A discriminative approach of directly estimating a function feels a little black box to practitioners often, because it's hard to have a physical sense of what it's doing. Okay, so naive Bayes, we were talking about categorical data. You have to estimate the class prior matrix, and you have to estimate the feature dimensional matrix, and this is too large a matrix, right? If this is two features, then it's too large. But if you assume independence, then things are a lot easier. And this is what naive Bayes assumes. It assumes that the features are conditionally independent. If x1, x2 is, this is just chain rule, and x1 given x2 comma y is the same thing as just x1 given y. That the second feature doesn't tell you anything about the first feature any more than the class does. If I tell you what the class is, it perfectly explains that feature. And in this case, how many parameters do we have? We have to estimate a bunch of such tables or vectors now, one for each dimension. How many parameters does this vector have? dk minus 1. Is it d times k minus 1? Not quite. So each of these is a conditional probability, right? So it's a vector of length 2. So there's only one free parameter, 2 minus 1. There's one free parameter in this vector. There's d of those that you have to estimate for every class. So 2 times d times k. So it's just dk. So we went from 2 raised to the power d to 2 to the power d times k to just d times k. This is much easier. You can measure 100 features, you can measure 1,000 features. Now the amount of data points that you need are sort of roughly proportional to d. Right? You don't need 2 to the d data points. Does that make sense? So this is doable. Okay. Let me stop here. What I'll do next time is we'll look at how do we estimate these. In fact, in your homework, what you're doing is you're essentially estimating these vectors from data, and the way you're estimating that is just by counting, and that's the MLE estimation that you've already proven in homework 1. So you already know how to estimate these vectors. It's just via counts. But we'll do that in class next time. Okay.